So let us see what is the difficulty with R. Okay, the difficulty is the following. So when you consider equations, so let me say difficulty with Q, or better, why Q is not sufficient for the analysis. So the problem is the following. If you have to solve equations like I don't know, first degree equation like x plus n is equal to m, then you end up easily with x is m minus n, that is in z, or if you have nx equal to m, you end up with x is equal m over n, provided that n is not 0, and this is in Q. So if you remain to this sort of first degree problems, you are okay. But if you go to second degree problems, for instance, x squared is equal to 2, the solution is not in Q. This is not a sort of abstract, not real, and purely mathematical problems. It has to do also with measurement and also with geometry. You know probably the legend or the history of Pythagorean that has to measure the diagonal of a square, and they were not able to do that. And it is a very nice story. There are many books on that, also some theater play that talks about this story. And you can also represent it in this way. You have a square whose side is equal to 1. So this is the square. And then you want to construct a square that doubles the area, and it is very easy because you consider the diagonal of the original square. Here it is very difficult to write down the exact diagonal, but however, it is easier to do it on the blackboard. Here the system is somewhat rigid, but however, even though it does not seem, all the triangles that are here are the same, but however, this area is equal to 2. So the area of this square, the blue square, is equal to 1. The area of the purple square is equal to 2. And now you want to know the length of the side of the purple square, which is the diagonal of the blue square, of the original square. So you want to know length like this. If you imagine to have a compass here and to take this length and put it here, this is the new length. Let us call it D, is the new length. So the idea is this square is equal to 1 because D is the side of the square whose area, sorry, this square is equal to 2 because D is the side of the square whose area is equal to 2. But what is D? And here there is a problem, and so there is a theorem that solves this problem, but it solves negatively. The theorem says there is no rational number D such that this square is equal to 2. Okay? Let us consider the proof. This proof is by contradiction. This is the first proof by contradiction we used. So, proof by contradiction says the following. We deny the conclusion and then we prove that the hypothesis does not hold. This is a proof by contradiction, and remember when we introduced the logical implication, we said that P implies Q is the same as non-Q implies non-P. Okay? So the logic is, instead of starting from P and proving Q, we start from non-Q, we deny the thesis, and we get to the contradiction with respect to the hypothesis. So deny the thesis. So suppose that there exists Z equal to P over Q, which is a rational number, such that Z squared, which is P squared over Q squared, is equal to 2. Okay? Now, this means that P squared is equal to 2 Q squared. Then, since P is 2 times a number, P must be an even number. So P is equal to 2K. Okay? Let me here be more precise. P and Q, we chose P and Q with no common divisors. Okay, this specific is quite important for the following. It is in general not said, we always mean when we have a fraction, this fraction is reduced to minimality, so there are no common divisors between P and Q. Okay, so let me just say P and Q have no common divisors. Okay, P is equal to 2K, so let us write again this guy here and say that 2K squared is equal to 2Q squared. This means 4K squared is equal to 2Q squared. So Q squared is equal to 2K squared. And again, Q squared as before, Q squared is even, then also Q is even. So there is a contradiction. It means that P and Q are both even numbers and it means that it is not true they have no common divisors, that P and Q have at least a common divisor, and this common divisor is 2. Okay? So here, if you want, the schema of the contradiction proof is more indirect. We really did not deny the hypothesis, but we added like that, starting from denying the thesis, we ended up to a contradiction. And this is how this sort of proofs works. Okay, so the proof is concluded. Here I put simply a square here, and so. The comment, what we learned from that, is that there are simple and natural problems, in this case a geometrical problem, that cannot be solved by rational numbers, only by using rational numbers. So now the problem is to extend rational numbers. Or if you want, informally, rational numbers have holes. For instance, I did not use this word, but square root of 2 is a sort of hole in the line of rational numbers. You can think of rational numbers like a line, and there are some holes. We will see how many holes and so on. The idea is to cover these holes, is to take these holes and let them enter in an enlarged set, which is the set of reals. This is the set of reals, and this set is will be our environment, our numerical environment for the rest of the course. Okay? And so let me give you the axioms of the reals. The axioms of the reals are more or less what you expect from our presentation. First of all, there are two operations. The sum, denoted by plus, and product, denoted by a dot. Okay? They are commutative, associative, distributive, with neutral element, with inverses for every element, with the only exception of the zero for the product. Okay? Second, This is another axiom I tell you. I did not insist on this concept. I take it as natural. But this set is totally ordered. Which means that for every couple x, y in R, with x less or equal, it is x less or equal y, or y less or equal x. So you can always compare the two numbers and decide which is larger. Okay, and the second, moreover, if both statements are true, x is less or equal y and y less or equal x, then the two numbers are the same. X is equal to y. And it is also important to stress the behavior of the ordering with respect to the operations. It is very important because sometimes students make some mistake on that. So, for every x, y, z in R with x less or equal y, then x plus z is less or equal y plus z. Notice that here the ordering is the same when we add the same number in both sides of the inequality. And this is a rule, this is, let me call it A. For the rule B, we have for every x, y in R, x less or equal y, and for every z in R with z non-negative, we have xz less or equal yz. And C, for every x, y in R, x less or equal y. For every z in R and z negative, here be careful because this times xz becomes larger or equal yz. So since we multiplied both sides for a negative number, here the sign of inequality changes after multiplication. Be careful of that. Okay? And now there is the last. Now there is last feature, last axiom, which is the most important here, that says that R is complete. This is called, of course, completeness axiom. Or Dedekind axiom. And this really makes what I told you before. We cover all the holes. We fill all the gaps of rationals. And so the definition of completeness is the following. Consider two sets, A minus and A plus, two subsets of R, non-empty, and such that for every x in A minus, for every y in A plus, you have that x is less or equal y. This means the following you have here. This red guy is A minus, for instance, and this purple guy is A plus. So what the axiom says is that there always is an element which is called a separator. So an element which stays between A minus and A plus, an element which is intermediate. This is the most important feature. So then there exists a psi in R such that for every x in A minus, for every y in A plus, we have that psi lies between x and y. This is the extremely important thing to be stressed. And this is what is not available in the case of rationals, indeed. So, the completeness is the feature useful to fill all gaps in the set Q. Indeed, let me consider this proposition. Proposition is a theorem, but I don't dare to call it a theorem because the property it states is not so fundamental, but it's a sort of exercise if you want. The proposition says, consider the two sets A minus is equal to all z in Q, let me say z larger than 0 to make things simpler, and square of z less than 2. A plus is equal to z in Q, again z larger than 0, z square larger than 2. So, what I want to prove is that there does not exist any, let me call it eta, not eta, I like eta to be used later, zeta, which is another important Greek letter, in Q, such that for every x in A minus, y in A plus, you have that zeta interpolates between x and y. So what is the meaning of this proposition? I said what is completeness. I said the reals are complete. So in the reals, there is such a number that does like that. I want to prove that in rationals, there is no such numbers. This is the difference between rationals and reals. Proof. Let us do it by contradiction again. Suppose that such a zeta exists. So there exists a zeta rational such that x, for every x in A minus, for every y in A plus, x less or equal zeta less or equal y. Okay? Now, since, as we proved, before, there is no rational numbers whose squared is exactly 2, it must be either zeta squared is less than 2 or zeta squared is larger than 2. Okay, suppose the first. Zeta squared is less than 2. This means that zeta squared belongs to A minus. Okay? Now, I want to show that there is another number eta in A minus such that eta is larger than zeta. So it is not true that for every x in A minus we have x less or equal than zeta. Okay? This is the logic. Here you have this rational number in A minus. I'm saying that zeta exists, it is in A minus, but I want to show that there is an eta which is larger than zeta. Okay? So, take eta equal to zeta plus 1 over n, with n to be chosen later. This is a difficult passage probably for you. You never saw something like that. But just follow me and then we will reason together. N to be chosen later. Okay? Then eta is larger than zeta, of course. We want to choose n in such a way that eta belongs to A minus, so eta squared less than 2. So we have to guarantee that eta squared, which is zeta plus 1 over n squared, which is zeta squared plus 2 zeta over n plus 1 over n squared, we want to show that this is less than 2. Okay? Okay, this is what we want to show. And so we want to choose n in such a way that 2 zeta over n plus 1 over n squared is less than 2 minus eta squared. Remember that 2 minus zeta squared is, however, larger than 0. So this is a second degree equation, and what we want to do is the following, is take 2 zeta n plus 1 less than 2 minus zeta squared n squared. So the inequality becomes 2 minus zeta squared, 2 minus zeta squared, squared is here, n squared, minus 2 zeta n minus 1 larger than 0. And so this gives us two roots that are zeta plus or minus the square root of zeta squared plus 2 minus zeta squared divided by 2 minus zeta squared. These 2 zeta squared cancel, so you end up with zeta plus or minus square root of 2 divided by 2 minus zeta squared. In particular, since here there is a sign of being larger, okay, a major sign, we can consider n larger than zeta plus square root of zeta 2 divided by 2 minus zeta squared. Notice that this is a positive number, and there always is a natural number large enough. Therefore, choosing n like an asterisk, we end up with eta in A minus and eta larger than zeta. Therefore, the number zeta cannot be the separator. And this is the end. On the other hand, the separator, by axiom, by Dedekind axiom, exists in the real, and it is the square root of 2. Oh. Okay, so this is all for this part. What is the spirit of this proof? This proof probably now starts being a bit complicated for you, but try to understand it, try to repeat it. Okay, don't worry, don't be scared of the fact that the logic seems to be new. It is new, it must be new. You are here in order to learn new things. Okay, this is good. And if you don't understand it fully now, then go back to that after some weeks and so on, and you will see that it is easier. And then I will move to the last part of today's lecture.